this. Yeah, it can't be isolated for right now, but something to be aware of, something I'm paying attention to. Let's see.
So what we do, most people
This one is better.
I'm sure it is.
That's an extra icon.
An extra icon? Which one? Yeah, but it's like the weird JPEG one, isn't it? It's not very high. No, it's like an SVG.
I don't know. No.
I only use PDF figures. It's a point of pride.
So our next speaker is Patrick Cook from FRIP, MSU, and he'll talk about parametric matrix models for nonlinear systems, the Gross-Patyevsky equation.
Great. So I guess I won't have to spend too much time talking about Gross-Patyevsky since Pablo briefly introduced it, but I promise I'll talk about the points that matter. But I want to do a quick history, as much as you could call the last year history, from where we started with PMM. So this is kind of the simplest classic setup. We have some Hamiltonian and then some perturbing interaction or some parametric interaction with this coupling constant C. And we want to emulate this, maybe extrapolate in parameters, maybe look at eigenvectors instead of eigenvalues, maybe do observables, who knows. And it's kind of obvious, or maybe it's not, that an emulator should just take the same form but be smaller. But we're going to come back to this. And so we did this for a while, and it turns out that this works really well. You're not supposed to be able to read this figure. You're supposed to go read the paper to read this figure. This is the premium content. So it works great. You can do all sorts of weird stuff. You can do phase transitions, and that's nice. But we want to go a lot farther. The title has the word nonlinear in it, so maybe that's where we want to go. But then we got sidetracked, or at least I did. And we realized, well, maybe this is actually a universal function approximator, just like a neural net. So maybe it turns out that eigenvalues are not just things that physics cares about, but maybe it's things that the real world cares about. And then I got really sidetracked, and I went and I did image classification. And so that's neat. And it turns out that these things are completely universal and perhaps more efficient than existing techniques. But there's no physics there. It's just kind of fun. So let's go back to doing physics. So how did I get there? You know, it seems obvious that, oh, I should just write down the same equation, but call it something smaller, right? So I've titled this section Epistemology, the philosophy of knowledge. How do we know this? But this question is more obvious when we think about, okay, let's do a different system. Anybody do nuclear reactions here? No? Okay, just a high order linear differential equation. You know, what does the PMM look like for this? And you can't just write down the same equation, or maybe you can. How would you know for sure that that's the right thing to do? And what if we did something nonlinear? So here's Gross-Patyevsky. What if, you know, I just wrote down the same equation, but said that all the operators and objects are smaller? How do you know that that's going to work? It doesn't actually. So let's go back just a little bit. So Pablo originally had concerns about PMMs in so far as, are these just RBMs? Are these just reduced basis methods? There's not really anything separating them from the rest of the field, maybe just some small practical or technique differences. And we disagreed, but it's hard to disagree concretely, right? How can we put our disagreement into math? And I think I've finally done it. I don't know if Pablo is still here or if he had to go for more important things. If he's here, you know, this is gonna be great. We're finally gonna be able to resolve our differences. So a typical reduced basis method says, take some data and take some representative sample of that data. The classic is PCA, principal component analysis using the singular value decomposition. But Dean's brother, who I didn't see on Zoom just yet, came up with he didn't come up with it, but he certainly popularized and published a great paper on the non-negative matrix factorization, which is another way to come up with these reduced bases, potentially better for certain systems. And there's, I'm sure, many, many more, but those are the two big ones. And you just use that to form some projection. That's this P dagger thing here, and project all of your objects down into this latent space onto those principal components or non-negative factors or whatever else. And you do this for all your operators and all your wave functions, and you call it a day. And this actually gives you a very nice structure. There are lots of very concrete proofs you can do using this idea of RBMs, and the choice of how you write your equations in the reduced space, what you're projecting down specifically, and what your projector is what gives you different RBMs. But what if I didn't know something? So hopefully, okay, the color does show up. I was a little worried about that. So I've kind of made H here representing a Hamiltonian faded. The idea is, what if I know that I have a Hamiltonian, but I don't know what it is? I know none of the parameters. This is a relatively reasonable assumption that I know that my system is governed by a Hamiltonian, but I don't know what each matrix element is. Can I still do this? Well, in typical RBM fashion, no. I can't project something that I don't know. But with PMMs, we say, well, I know that such an object must exist. And so I can just learn it directly. So that's this underlined dark green M, is that I'm going to train through some training algorithm very similar to what neural nets do. I'm going to train this new smaller Hamiltonian, and I'm guaranteed to have such a smaller Hamiltonian in a latent space because I know that I have some snapshot basis, and I know that my system was governed by a Hamiltonian. I just didn't know what it was, so I couldn't project it down. But we can go one step farther, and we can say, what if I didn't even have those snapshots? So now everything is light green faded. I don't know what my projector is. I don't have snapshots of the wave vector, but I have to have data. So I have data that is maybe some macroscopic property of the system, an observable, a density, who knows, some way of sampling the underlying system. But even if I didn't have snapshots of the wave vector, I know that those samples I took could have or would have come from a wave vector. And those wave vectors, if I had them, could have made this projector, this snapshot basis. And so I can still do everything here, right? I know I had a Hamiltonian, didn't know what it was. I know I could have had snapshots, but I don't have them. But I know if I did have them, I could have done this. And same thing here. I can't make my smaller wave vector by construction, but I could learn some effective one just by training on the data, some gradient descent method. So this is the implicit coined term, patent pending, I don't know, we'll call it something else eventually maybe, the implicit reduced basis method. As far as I can tell, that term hasn't been used quite that way in literature or at all in literature, so I'm going to run with it for now. So this is kind of the foundation for the theory of PMMs, is this implicit reduced basis method. That is that the snapshot basis or just the latent space basis is floating. It's not fixed. It can be kind of semi-fixed, or it can be completely undetermined, like in this case where I don't have the snapshots. So we go back to the original idea. This is what it was. We did not know what the Hamiltonians were, what the pieces of the Hamiltonian were. We just knew that it existed in this form. So the things that are in black, we know for sure. And the things that are in light green, we only knew that the equation was in this form. We don't have the snapshots because maybe we're only training on energy. So this is a macroscopic observable from the state, or rather from, I guess, the Hamiltonian directly. And so we can't actually just project this Hamiltonian down, even if we knew H naught and Hi, but we know it would have this form. And I can start grouping these things together, and we know that they're going to be smaller. And so I get my PMM, and I'm guaranteed that this will work. And I can use all of the nice constructive and direct proofs from RBM theory to prove things about PMMs, which is great. And by prove things about PMMs, I mean just rely on all those other proofs and say, this will work too. So now we can start answering questions on what do we do for harder systems or different systems. So this is some weird tensor diffie-Q. This is what you use for reaction networks. And I will not know these reaction rate matrices or tensors, but maybe I'll have snapshots of the density as a function of time, and I will save all the math. It's ... But it turns out it's the exact same form. This is very nice. And this just falls out of the fact that this is linear, but in higher dimensions, so it stays in the same form. This is great. What about nonlinear things? So let's start with the easier case and maybe less realistic case of...
That's not linear, right? The previous equation.
This is linear. It's in a higher dimension.
Linear is not linear in terms of P, right?
No, it's linear. These indices aren't shared. If this lower index, mu, nu, and tau were all the same index, then it would be nonlinear. I agree.
So this is anti-symmetric, this tensor S, or if it's zero, if mu, nu, and tau are the same, right? Or two of them.
Yeah. You wouldn't have them like this. It's just from reaction networks. You can write this in a very, very high dimension that is exactly linear.
Yes, so Sulama is
Correct.
working on this, so I know this. But then in terms of vector notation, it's really the vector to the third power.
I can't hear you.
In terms of vector notation, it's really a vector to the third power. So it's not linear. You can't scale like a vector by a constant. It doesn't change any equation.
Oh, sure, yes, and yeah, absolutely. But yeah, okay, so in that sense, it's not linear. I've overloaded these terms. Okay. Good small point. I did forget to mention, please do interrupt me with questions. I don't want to do the questions at the end. I'll forget what I said. So, okay, so the simple case of a relatively simple case of having snapshots of the wave vector, but some sort of nonlinear governing equation. So this is Gross-Podolsky. It doesn't matter why or what or whatever else. It's just that it has a nonlinear term. So we have our standard kinetic energy operator, some trap potential, external potential, and then this interaction term where the wave function interacts with its own density. So if we had snapshots of psi, we can actually project this weird nonlinearity down. It ends up becoming just a higher order linear operator it's just a tensor with a bunch of indices. I had to switch to index notation, otherwise this doesn't make any sense. And this is all from just using the implicit RBM idea that we can get an exact expression in a latent space every time. And it turns out this works. And so since we don't have T and V, we'll have to learn them. And the same thing with the tensor that ends up representing the dot product here, or the direct product here. But what if we didn't have those snapshots of the wave vector? So this is a more realistic scenario. But we do have the density. Well, we know how we go from...
Sorry, go back to the dream slide. So in this case, it is really non-linear because this G doesn't have to be anti-symmetric, or you can have I with, sorry, J equals to K.
Yes,
right?
this is right.
So basically, you're saying, I mean, if you insert Pythagoras P, the projection, you need to, but that is one in a sense, and this is how you get this equation, I guess, right? I mean, it's psi cube, but then you need to project each time, and you confront psi with psi, the full psi. You insert a Pythagoras projector in there, and then you get this more psi. Is that the idea?
Yeah, and you can very carefully, by associativity, group things down so that all the dimensions of that G are in the latent space. Okay. You never have to go back to the full space.
That's okay. That is my thought.
Yeah, so if you've seen papers on the proper orthogonal decomposition on doing these sorts of nonlinearities, they usually go back to the full space, do this nonlinear term, and then project back down, which is very inefficient.
Yeah, that is what I was wondering. You never have to go back to the full space.
In theory, you can construct this exactly using those projectors, but it's too expensive. It requires computation.
Oh, so basically you're implicitly assuming that you could do that, and you're instead learning it.
Exactly. And then we can also decompose these with tensor networks to make the number of parameters really small.
Yeah, but JKL already it's in the small space already, right?
Yeah, but if the PMM is 10 by 10, this is 10 to the 4 number of parameters naive.
Okay.
So it's rough. We want the PMM to scale as the latent space cubed at most. Well, the evaluation cubed at most. The number of parameters should be squared. Okay, thanks. So the same equation, but now I don't have snapshots of the wave vector. I have snapshots of something else that I can make from the wave vector. I know how that's done. And so it's kind of, like I said, it's a way to probe the underlying system. What's important here is that I can't just use snapshots of the density to construct some reduced basis for the dynamics of the wave vector. You can convince yourself that you can't write down any differential equation in terms of only the density for this. If I add an arbitrary phase to my wave vector, I introduce a whole bunch of momentum, potentially, that is not seen in the density. And so there's no differential equation just for rho that will actually work. So I have to do something a little bit more complicated, but it turns out it ends up being the same thing. Basically, you apply the projector for rho that you know, and you apply the projector for psi, which you know could exist, or actually you know exists, but you don't have it. And you start grouping things very carefully by associativity such that all of the operators you need to learn are only in the size of the latent space. The only extra thing here is that we'll have to learn some representation of each initial state that you care about. You can parameterize this however you need. And this also works. So that's the broad strokes theory. See paper eventually for the really grindy math, I guess.
So where does QI there?
This is the latent space density instead of rho. Just give it a different name.
You learn the density between the density and the psi here.
You got to speak louder.
So you learn the density, the relation between density and phi.
Yes.
Okay.
And that will allow you to reconstruct little psi, or you never have to materialize little psi?
You will materialize little psi, but you won't be able to project it back to the full space because you don't have its projector. You didn't have data for it.
Yeah. But to do it, you do need to reconstruct the phase in a sense.
No, not in the full space. Nothing
In the reduced.
in the reduced space. You will end up learning the phase correctly.
Because of the equation itself.
Yeah, because we know it's governed by this, which has to deal with the phase.
Okay, and then, sorry, do you know the initial condition? The initial condition, you need it with the phase or not?
You will learn it with the phase. Yeah, you constrain it so that it reproduces the initial density, which is something you would have to have here.
Yeah.
But it could have whatever phase it needs to have to fit the rest of your data. And so theory is nice, but results are better. Which button am I supposed to press to go next? Okay, so let's just consider the simple case where I did have the wave function data. So we're not doing that density nonsense that I talked about just a minute ago. This is something that other methods can at least attempt to do. Right? The only having density data, other methods can try their best, but fundamentally they can't actually, systematically improve to the exact answer. This, on the other hand, this is going to be with wave function. So here's the exact toy system, if you will. I start with some Gaussian wave packet offset from some trap. It's self-interacting, Gross-Podolsky, like I said, and it just evolves in time. So time is the x-axis and position is the y-axis. So x is the y-axis. That's great. And then this just shows the density in good old MSU green. So if I give this to DMD, dynamic mode decomposition, which I think many of you should be familiar with. If you're not, it's kind of the standard approach to any of these time series methods. And I cut off the data that it has available at this red dashed line, it basically falls apart. So fundamentally, it's a power iteration method. So we'll converge to some steady state. Whether that's right or wrong is up to interpretation, I suppose. And it works relatively well for reconstructing data it's already seen, but is, abhorrent when it comes to time extrapolation. This is a well-known property of DMD for the most part. If I do what I just mentioned in the previous slides with a PMM, it's just amazing. It actually has less data, so it only uses before this first dash line for training. In between the two dash lines, that's validation, and then everything else it's never seen before, and it extrapolates out in time. And if I highlight where we have these really, what I will say is the manifestations of the nonlinearity, these extra dense regions, you can see that DMD, even during the training data that it reconstructs, it's not very good, where the PMM is very, very good.
Patrick, so DMD has a generalized version, right? Try to take into account, yes.
Yeah, so you're talking about Cindy?
Not Cindy, like you can try to take into account some nonlinearity, like you showed, into the linear space.
Yes, so there are a couple methods to do that. Neural operators and DEIM, which is the discrete empirical interpolation method. But fundamentally, these are all linearizations of a nonlinearity. Right? So you're going to lose some information no matter what you do.
But the thing you are comparing is the basic DMD.
This is a package that everybody uses, standard Python package that everybody uses.
Red regions.
Sorry,
We have these red.
yeah, so everything to the left of this data.
No, not the lines. In the waves, you have red stuff.
That's just what I call the manifestations of that nonlinearity. You wouldn't have this without the nonlinear term. They're extra dense regions. So it's where a method that doesn't reproduce the nonlinearity is going to fail the most. All right. This is a relatively simple problem. The harder problem is now. So now we actually want to do this parametric and with only density data. So again, I mentioned before that other methods don't have a systematically improvable way of reconstructing some effective system of equations for this. But also, I didn't do anything parametric yet. So is it really parametric matrix model? So we'll do both at the same time. We'll do something that can't really be done with anything else. And we'll also start varying all of the model parameters that we can. I'm omitting here that you can also vary the initial state. But for this, we won't. And so we don't know these operators. I don't know the momentum operator. I don't know the position operator. And I'm going to say I don't know my wave vector either. But I know that everything has this form. And I'll have data for the density. This is the exact case. This is one of the exact cases. I've picked some values of the mass, the trap, and the self-interaction. And I cut off the data here, so everything to the left will be trained, everything to the right will be withheld and tested on. So if we use a very standard off-the-shelf, very, very popular package, PyDMD, and we do parametric DMD, so it gets to see all of the data for all of the different samples of the model parameters, this is what it reproduces for that specific example. It's kind of the same story as with normal DMD, with the non-parametric case. It really, really struggles at extrapolation, but it is incredibly good at reconstructing your training data from a very, very reduced space. So it does what it says it's supposed to do. But if we do the same thing that I said before, but now with only the density data, learning all these weird tensors, the PMM basically nails it. And so this is something that, as far as we know, other methods drastically struggle with. I do want to highlight that the training region is actually only half of the data that it was given. So in a sense, the parametric DMD had twice as much data, but we do use this data for validation. So it's not an exact comparison.
So this is somehow a very regular pattern. So what about if you had more than one frequency?
Yeah, absolutely. Yeah. So part of why I highlighted previously these red terms is because while the overall linear trend is from the linear dynamics is very periodic, these high density regions do not have the same frequency. But I'll get more on this later. I don't have a lot of figures to show on that, but that's still perfectly doable. Daniel.
When you're doing the parametric parametric PMD, it looks like the high density regions are only there in the training set.
Yeah, so it struggles on this when we don't have the wave function data, but we only have the density data. It is not as good. But the trade-off here is that this is also over a vast array of parameters, not as before where it was just trying to reproduce one thing. All right. So okay, figures are cool, but numbers are better. Some concrete objective numbers looking at how well things do. So if I run through the simulation in time, and I just compare the two methods, the average over all the different parameters that were sampled and the standard deviation with that, the PMM has this really nice predictable growth in its error. Of course, it's going to get worse over time as we get farther and farther away from our training data. Whereas, as mentioned before, parametric DMD, basically as second it starts trying to extrapolate, it fails. This is a relatively well-known phenomenon with various DMD methods. It can be improved via, like I said, neural operators and DEIM, but for now we're just trying to apples, not apples to oranges. And then, again, if Pablo's in the Zoom call, he'll love seeing this as a cat plot. So we're going to look at how long it took to do an inference on the x-axis and how much error was in that inference on the y-axis. And then I've done it for 3 different snapshot times. So this top one is within the training data. So if we look at blue for the PMM and orange for DMD, the PMM is faster by a couple orders of magnitude, but they basically have the same error. DMD does slightly better in the training data, which is what we saw in the figures as well.
As previous figure, so it looks like the error grows exponentially in time, but I did not see this in your nice plots.
This is a artifact of the error metric that we use here. So KL divergence is basically how much it's an entropy-ish measurement. So this is already kind of hard to think about. It's how surprised you should be if you thought your distribution was something and then you measured a completely different distribution. So you'd have no surprise if they were exactly the same, 0 error. You have lots of surprise if you sampled something completely different from what you thought was some other distribution. This error, yes, it does grow exponentially, but if you looked at other metrics, it wouldn't. It's very hard to pick an error metric for probability densities that is super interpretable. But that's why we're only looking at the difference between the two methods.
Okay, we can try doing the same analysis when you have the wave function itself. I mean, does it grow like that? It's much smaller, but does it grow the same way exponentially?
That's a great question. I don't know off the top of my head. I'm sure I made that figure at one point. Off the top of my head, no clue. But also for the wave vector, I don't think we don't use KL divergence with that because we have the wave vector. We don't need to do.
Yeah, but you can still compute it.
I could, yes. Yeah. I probably
just just to see whether having.
I might have a figure on a different system later that does that. We'll see. Am I gonna run out of time?
It's 22 minutes so far.
All right, stop asking questions. We'll just skip this. It does good. It gets better at later times. Snapshots compared to DMD. It always stays very fast. Okay, so let's move on to 2 dimensions where Gross-Podevsky is very interesting because people in condensed matter really care about this because Bose-Einstein condensates do all sorts of neat stuff. And we're going to see if an MP4 embedded in a PDF from LaTeX will play. I know that sentence will end me in a very bad place when I die. But oh, it's real high frame rate, huh? That's Zoom. I promise it's so smooth here. It really is.
Turn the laptop screen around.
Yeah, that'll work.
No, you can see.
For the people in the front row, you want to see the smooth version of this? Either way, so this is the same-ish thing. This time I did use wave vector data mostly because it takes a little bit less data and it's easier to just get stuff going with this. So this is with wave vector data, but in 2 dimensions. I've sampled over all sorts of different parameters for the system and initial states as well. I give it some initial angular momentum, different angular momentums across the data set. And this was in the test set. So it's never seen this. So the exact thing is up here. So we've got the wave function with its phase and color, and then the density, even though this also contains the density information and its brightness, but it's nice to have them separate. And this evolves for 4 times as long as any of the training data ever evolved, and validation data as well. So its validation set is this much, and the test set is this much. And also, it's never seen this initial state before. It's never seen these parameters before. And it does quite well. Will it go to the next slide? I think that's the next slide. This is another one. I have to show these because it took me so long to make them. So this is an even higher angular momentum state. Yeah, this frame rate's awesome. And again, it's the same story. So this looks great visually, but of course, we want concrete error metrics that are definitely interpretable and not weird entropy measurements, but we're going to do that anyway. Okay, so if we look at across all the parameter sets, the 500 to the left of this dashed line, we're in the training data. The 400 to the right of this dashed line, we're never seen. Test data and everything in between is validation. The order is arbitrary. And mean squared error is a bit more understandable. Mean squared error in the wave functions is a little bit of a weird thing, but either way. The important part to take away here is that there isn't a trend from the train to the validation of the test data of the error increasing. It kind of doesn't care. It really has learned the underlying structure of the Hamiltonian, if you can call it a Hamiltonian since it's wave vector dependent, which is great. So extrapolation in parameters is basically spot on. Let's look at time. This is more or less the same story, but this is not KL divergence, this is mean squared error. So I was wrong, didn't have the figure you wanted, I'm sorry. But it's same story as before. As we get farther and farther from the training data in time, it does get worse and worse, but importantly, it's very smooth, predictable, constrained, and stays low enough for all your needs. I don't know what needs you have. Okay, so this is the final thing. Hopefully I'm still within time. Danny, can I take a whole bunch of your time away from your talk? So this is the how I want to think about PMMs moving forward. It is not, I make some sort of model that produces an eigenvalue and I fit that eigenvalue to whatever data I have. While we did prove that that is a universal function approximator, so too is a neural net. Why not just use the neural net, right? What a PMM should be is a brand new class of methods that fits in with everything else. So one idea is equation-free methods. I don't know what the underlying equations are. This is DMD. DMD just says, let's just make it linear somehow. Cindy is also this, where it's, let's make it linear with nonlinear, a linear combination of nonlinear functions is what Cindy ends up doing. And neural operators are the same thing, where it's, let's just make it a neural net. Right? So we don't know what the underlying equation was, or even if we did, we're just not going to use that information. The other side of the spectrum is I know exactly the equations. Not just the form of them, but I know all of the elements of my matrices. I have all the information I could want. I just need to do it in a smaller space. This is POD, the proper orthogonal decomposition. It's also eigenvector continuation. But the stuff in the middle is really powerful. So you can make a PMM that's just linear, that's just an eigenvalue, that just takes no information about the underlying equations. So that would be on the left. You can make a PMM where you construct all of those operators. You don't learn them from the data. You don't do gradient descent if you had all that information. But what's really the core essence of a PMM is this middle ground where I just know the form of my equations. I know the form of my equations. I know how I probe the data. I know how I get from the underlying state vector. Doesn't have to be a wave vector. This can be done in classical mechanics. I know how to get from that to the data that I have. And this is where I also say this is an implicit reduced basis method. So that basis is floating. It's not fixed like it would be in most, I don't want to say all because I haven't read every paper in existence, other reduced basis methods. That's it. I'm going to just let this play instead of leaving it on like a thank you slide. But I thought this would be nicer because it would have a frame rate that was, didn't give me a headache. But maybe that's not good.
Are there questions? Yeah, very well, quick question. In the time-dependent equations, I think you're saying the training data is the density, time-dependent densities. So you don't have any data on the wave function.
In the 1D figures I showed, yes. In the 2D figures, I was using wave vector data.
Yes, because the phase, right, the wave function, the phase, the time dependent phase actually is very relevant in the equation.
That's what I said.
You have ddt on the wave function. That phase is actually physical.
Yes. So because you have this time series data, it is able to reconstruct that phase in the latent space only. You can't bring it back to the full space though, because you didn't have data.
But actually, time dependent DLT tells you there's a direct cover, there's one-to-one relation between wave function.
Yeah.
It's kind of abstract, but
It's not impossible. Clearly, it's not impossible because I did something. But with these direct reduced basis methods, you would lose that information.
Okay.
Yeah, so thinking about your long-term behavior for the 1D things, for instance, where you see the smearing at large times, are there ways to impose certain constraints in the time evolution? So like the continuity equation is something that you'd expect to maybe make sure that you don't lose particles, for instance.
You're talking about with DMD.
No, well, with your PMM method too, can you impose, like, is there a way to ensure that you're not losing particles, for instance, or energy conservation, all these things?
Yeah, so the PMM has that for free with just the wave vector normalization in the latent space. You're guaranteed that the L2 norm specifically is conserved between the full space and the latent space. And that will usually, I'm trying to remember all my mini body stuff, give you, your conservation laws. You can force more of them in, right? If you know you have some symmetry, you can make its generator, right? E to the I symmetry, and you can impose that as well. And since that transforms the same way that anything else does to the latent space, you can put that exactly in the latent space. Does that answer your question?
Kind of, yeah. So the continuity equation is the one I'm thinking about, where you have, that's the generator for your particle number conservation. If that is being adhered to in the long-term limit for like the 2D plots, for instance, that we're seeing.
Oh, you're asking, is it even if I haven't imposed it? That's a good question. I can check that. I can say that, and this is maybe tangential, but so I didn't show it here, but we can learn a Lagrange multiplier that we didn't see from the original equation. So let's say that the L1 norm had to always be 1 in the full space. That is not necessarily conserved under this projection, implicit projection. And we will say, okay, well, we can't project down the Lagrange multiplier term. So we have to learn an effective one, and we can do that exactly in latent space to force conservations.
real quick. Yeah, so
And he said I could use all this time, so it doesn't have to be quick.
So for the time dependent equations, right? So what is the dependence of the trained model on the initial conditions? So if you vary the initial conditions, do you have to retrain it, or do you actually everything wrong?
No, so it's the classic problem though of if the new initial state that you want to predict for doesn't have significant overlap with the data you trained it with, then you can't do anything, right? So think about, if I give it a new initial state and the overlap with all of the training data was 0, then I can't do anything.
Oh, so your training data does have different initial conditions.
In the 2D case, yes, that I showed, but we could have done it in the 1D case as well. Different examples.
Okay, get it.
Yeah.
Let's thank Patrick once again.
Let me leave.
Oh, yeah, what?
I'm gonna use my laptop. It's my laptop.
Are you the one who's gonna project?
You put it on the Google Drive.
Yeah.
Oh,
So him, maybe?
Yeah, well, him is, okay, I don't know if we're gonna,
Gonna
Or
work?
Google Drive?
maybe it's
If it
best,
doesn't, that's fine.
you want me to do it? I can try to do that, and then that's for you. Oh, this is the pointer, you mean?
Yeah, I just wanna plug in the pointer somewhere.
If you just want to, he can change the slides if you just want to use the link there. You don't need to plug it in.
I'm thinking how to access.
Yeah, you can change the slides for me. I'll just use the pointer program to point.
How about USB-C adapter? I thought you were gonna use your laptop, Danny.
Here, I can do the slides. Okay, I'm opening the.
How many?
I'll just use this as a pointer.
does it take? Let's see if any of our undergrads are in the Zoom call. Who gets brownie point?
You see? Okay. I got Streamline up there.
That makes it better.
Yeah. And look, it just fits perfectly right under the 8. No, yeah. I didn't do that, it just magically happened.
That's what LaTeX is for. You don't have to do it.
All right, our next speaker is Danny Jammooa from FRIP MSU, and he'll talk about parametric matrix models extracting non-perturbative ground state from first order perturbation theory.
For the introduction, I will not talk about that title until like the second half of this talk. Yes. Next slide.
Oh, yeah, that's me.
I already did so much work. Why are you making them more work?
Not responding to me right now for some reason. Okay, why is that? Okay, it's just slow.
Do you have a place to put a dongle? Oh, no, you haven't. No. So quick background. Ab initio methods are crucial for understanding quantum many body systems. You could just click the whole slide. I won't do that. I won't make you do it. Just click through the whole.
But he doesn't know when to stop it.
Yeah, well, until the end. That's the last one.
That's what I meant, yeah.
So the main obstacle is actually treating these complex interactions. The difficulty is based on method dependent. If you're doing a surgical cluster, it's how you handle 2-body or 3-body forces. In lattice CFT, it's the Monte Carlo sign problem, which manifests in Euclidean time data. Why does lattice CFT use Euclidean time data? For example, if you want to do direct diagonalization to get the full spectrum that scales cube. If you're just interested in a specific state, you can do real-time evolution, Trotter or Krylov methods, but that also scales exponentially. Due to cursive dimensionality, the Euler space grows, which means you probably can't even store the eigenvectors in memory, and it becomes prohibitive to do these methods. However, with imaginary time evolution, if you're just interested in the ground state, you can implement this stochastically. Monte Carlo will bypass the large size, the full space storage problem, but your lunch is a sub problem. So, also free to interrupt me. So what is imaginary time evolution? Well, given an initial state, you can propagate. Is a non-unitary propagation in imaginary time tau. You can decompose the initial state in the eigenbasis, and what you see is it will project out the ground state because it will filter out all the higher initial states because they will decay exponentially faster. And since this is what lattice CFT does, we wanted to see how can we implement use PMM to assist. One, which is the most basic idea, is in early time data you extrapolate. The second one, which is the title of the talk, I'll get to later. So say you have this Hamiltonian that's you have H naught and HI. In lattice CFT, what they do is they group all the terms that would not exhibit the sign problem into H naught, and then find its ground state, and then they would do first order perturbation with the energy correction for the interaction that would result in the sign problem. Well, you can generate the data from your governing equation on the left, and then on the right, we could just do the same thing with PMM. However, in this case, we will be learning an initial state. I don't have it turned on. We will be learning an initial state because we won't have snapshots of wave vectors or whatever, so you can make a projector because I don't think they even store the wave vector. So you get the energies, you minimize it, go some loss function, maybe MSC, whatever, and then you can extrapolate to the asymptotic region. So here's some examples. Each row is a different system. Each column here's the first column is just the ground state. Here's the first order correction. We compare it to an exponential fit. The black dots are the training, and the green dots is the test net. And we can see, we do as good as the exponential fit.
Why do you use an exponential fit to compare it to?
Because it's just a sum of exponentials.
What do people do in practice?
Yeah, the exponential fit.
Okay, thank you.
That's what I said. Whatever. Well, the PMM probably did as good because it is also just ends up being a sum of exponentials anyways. We tried a harder interaction. We only had data for the later time for C12. We see that the PMM does pretty good there. The exponential fit overfits, but we don't have data for the other ones. We see a similar trend from oxygen 17 to 20, but I can't really make a claim. We have one example, but is this really interesting? Just, I mean, the exponential fit does a good job. Everyone uses it. So why are we trying to redo this? Can we do something more interesting? Before I get to answer that question, I'm gonna talk about the simulation I did to synthesize the data, to generate the data. Say you have, here we have two charged particles in a 3D lattice, the periodic lattice, and the Hamiltonian consists of a kinetic energy term, a delta function potential, and this R-sphere wall that's far away from the origin, just for a stability region. We can regroup the Hamiltonian to H naught, and then the attractive Coulomb interaction in HI. I'm not saying that this results in a sign problem. I'm just trying to emulate what would happen from a quantum Monte Carlo. And then we'll take expectation values with different initial states. And we will propagate this initial state using just H naught. And then we can calculate expectation value for H naught, HI, and maybe some observable you're interested. Here's the density. So I'm just going to rewrite that again. You have different initial states. We propagate them, take expectation values for the PMM. Well, we don't have the initial states, so we'll just learn K initial states or I initial states. We'll propagate it through a learned matrix M naught, and then we'll take expectation values with these learned matrices M naught, Mi, and the density P in this case.
So the training data are still matrix elements, right? M of T is what you use to train, right?
Yeah, M naught, the psi.
Oh yeah, but these are your
MI
training,
and P.
what you're gonna learn.
Yeah,
But
so we'll learn.
sorry,
The data will be the expectation values
Okay, because in
for
principle,
different initial states.
sorry, in principle, it's true that you don't have access to the wave function itself, but you do have access to, say, the densities. For example, if delta is, the operator is 1, for example, I mean, you can get access to, say, as in the previous talk, right, the densities. And I was wondering if you would, the distribution, say, normalized, but I don't know if
I just kind of think of this
because
because I want to choose an observable. Maybe in a specific case, yes, you can just construct the. Is that what you're trying to say?
I was wondering if you tried to use the
No, I
density
didn't.
as it, okay.
I didn't know. So the question is, all this data that we'll be giving to the PMM to learn will only be as a function of time, and can it predict the ground state energy of the Hamiltonian as a function of C and expectation value of rho for any function of C without seeing any non-perturbative ground state as a function of C? Can it do that? So basically what I'm saying is we knew that the form of the Hamiltonian was H naught plus HI. So I'm just going to write the PMM as M naught plus CMI. I'm going to do the eigenvalue decomposition, which will give me the energies as a function of C, and the ground state of the PMM as a function of C, which then I could calculate an expectation value of this learned observable rho. So the first example is there was a deep delta function in the center. So there's a bound state at H naught, so that's C equals 0. And here I fit a polynomial around 0 to get first order, second order correction terms. We see it does pretty good for the bound state, but once you exit the bound state, it doesn't really get this kink over here, or the trend. How about a PMM? Here I did a 2x2 PMM all the way to a 9x9 PMM, and all cases it was able to predict this kink to the left of negative 0.3 maybe. And again, it never saw any data of the non-perturbative energy as a function of C. It just saw the time evolution as a function of the imaginary time. So which is pretty interesting that it could do that. And then here, on the next slide is aerometric. And on the right side is I took the expectation value of the two different observables. The first one was I had a density function around the origin, which is in blue, or the dotted. And then the second one, I had a density function far away from the origin, which is this purple or dashed line. And we can see that the PMM was able to extrapolate from to -1 and 1 in both cases in energy and the ground and the expectation value of rho in the ground state. And again, it should only do good around c equals 0 because we evolved the states in H naught, but it was able to predict the it was able to sum up perturbation theory and did a pretty good job. Next slide, same Hamiltonian, but this time H naught did not contain a bound state. And if we do, if I do a polynomial fit around 0 and plot what would be first order, second order, third order correction, it failed both the left and right. How well does the PMM do? Well, as n increases, it systematically gets better in both regions. And then use an error plot. Again, same story. I don't know if this what method I could even compare to in these plots I've been showing. But one thing, maybe going back to the previous two talks is, or the previous talk is, what's a good error metric? For example, here is just, I'm taking the average and the standard deviation of 10 different PMMs that I trained that are both the same size. And that's how I got these error bands. But what if I just took the mean result and plotted it? I didn't put it in this plot, but it's another order of magnitude better performance. And then next slide. Another thing you can do is extrapolate to the complex plane. So we extrapolate in real C, but then also extrapolate in complex C. And we can see that it did a pretty good job, pretty good error all around. Maybe just the slivers over here where it had 10 to the -1. But all this results that I showed can be even systematically improved even more. The next slide. Currently, like I showed, the data I used was expectation values, but we can probe the action of HI still within first order perturbation theory framework by expanding the data to include transition amplitudes and two-time correlators. So now we have our data consists of this MIJ. And I don't have results for this, but for proof of concept, I was working with the Heisenberg model. And I showed that if I included this data, we get systematic improvement. And this is, like I said, it's still within the first order perturbation framework. So the data to obtain this data is not going to be more expensive. It's going to be as expensive, maybe cheaper. But I don't know. I don't actually know how this is done. So maybe someone can tell me. Okay, well, for future work, while this benchmark example goes back to a simple particle system, the same method is used for quantum many-body simulations, which so far has been limited to first order perturbation theory. And that is what we're currently working on implementing it for a quantum many-body system. That's it.
Okay. Questions? Yeah.
Okay. So maybe you are aware, but Mike Bachman at Fermilab, he tried to use, not really similar in spirit, but he tried to use lunches. Basically, to use lunches to improve on the exponential fit on his lattice quantum Monte Carlo data, lattice QCD data. And this would be, a nice application would be to apply this to lattice QCD as well. Because the same way, it's practically the same thing. Basically, it was trying to construct the Lanczos matrix by taking not diagonal matrix elements, as you showed in your last slide. If you just take diagonal matrix elements, you can't really do it. But if you take tau I, tau j, you can actually reconstruct. Yeah, this one.
I mean, it still worked with the expectation, but it will improve substantially.
The question is that once you get the separate question, once you get the say with PMM, you get a reduced base Hamiltonian in a sense. In principle, you will get excited states out of it.
Yes.
Did you try diagonalizing it and see how far you are from excited states with the same quantum numbers, of course?
Yeah.
Still only training on the ground state.
Yes, because you start from something at tau equals 0, which is contaminated by excited states.
Yes.
And if you then exponential fit,
Oh, yeah.
you get the energies on
I don't think I mentioned it, but I train on the whole evolution. So early time and late time.
Right, so early times are contaminated by excited states, which in your case would be your sigma.
I did not check.
So in principle, your Hamiltonian knows about the excited states with the same quantum number of the ground states, of course, right? So maybe that could be a nice application. If you diagonalize it or get the lowest eigenvalues and see how different they are from a multi-exponential fit.
My guess would be I haven't tested it, but my guess would be probably the first excited state close to around zero.
Sorry?
Close to around zero, but probably can't extrapolate too far in C.
Oh, no, I'm not talking about this already in C. Say you do,
Oh, just H naught?
even
In tau.
in general,
Oh, in
for a
tau.
given Hamiltonian, you train on different, I mean, you get this H.
Yeah.
And suppose, forget about H naught and HI, you have just one H. For us, the problem is extracting excited states. And people typically do, they sample multiple exponentials so that they can get the excited state energies, but that doesn't really, I mean, it works, but kind of. In your case, instead, you could use PMMs to train on Dr. lattice data, then diagonalize this reduced basis H and get excited states out of them.
Yeah, I mean, I could test it, but I'm assuming it's probably at most is first excited state would be the most accurate.
Yeah, earlier when you were comparing against the polynomial fits.
Yeah.
It looked like the PMM was getting some of the qualitative behavior, but maybe not so much the quantitative behavior. Do you know why?
Good point.
Something like that.
Yeah, so any
No,
if you-
forward.
next slide, please. Yeah, so you're seeing the qualitative behavior, it's gotten the phase change, it's gotten that change, but it's not getting the quantitative behavior, right? Is that just because you don't have enough training data, or
What do you mean by quantitative?
it's not on top of the dashed line,
Oh,
even when you have a number now?
oh,
It's hard to
so
see, there is one that is.
Oh,
there is one that is, but also I chose a single one. If I did statistics on it, it would be within the
Okay.
standard deviation.
Okay.
It's also, if I may, so it's really important to point out that, again, the only training data is at C equals 0, and that's a phase transition.
Sorry, so you only have one training?
No,
No.
my
One
training was
training
a
point
function
in
of time.
C, many training points in the
Okay.
Euclidean time, but it has never seen anything that
Right,
involves
so
time
the
evolution.
qualitative
linear.
behavior in itself reasonable.
I mean, the fact that it can go past the phase transition to begin with is phenomenal, but yeah, there, again, if Nady did statistics on it, or
It would
if he
be.
didn't pick light blue, you would see that there is one that applies for.
Okay.
But the reason is that, again, I think you're capturing excited states of the non-interacting case,
Yeah,
and they
or-
form a basis for the.
Exactly. If the density of states is not too great,
Yeah.
we have a representation, approximate representation of the low-lying states of H0, the unperturbed Hamiltonian. And he's getting the matrix elements of the perturbation. And if he diagonalizes it, he does a pretty good job.
Like second order perturbation theory and beyond.
Yeah, exactly.
And then I also had a question on the lattice EFT. When you make this decomposition into H naught and HI, do you know ahead of time which parts of the Hamiltonian are responsible for the sign problem?
You'll have to ask him.
We argued in the car all the way here.
I have no idea about that.
Yeah, so we understand which terms give the sign problem.
Okay.
I have a question, if that's all right. So in your unbound case, Dean,
On the
would
other
you
one.
slide forward for me?
I'll try to get this working for the next talk, okay? The afternoon should work. Sorry.
Dean makes us do work all the time, so now we're gonna make him. So you've trained on an unbound state, an
Yes.
unbound case at least.
Yeah, so the initial H naught does not have a bound state.
Yes. Does this mean that you could make your H naught just a free particle, the kinetic energy, and put all of the physics into HI and do the same thing?
I mean, the only other term H naught had was the wall for,
Did it not have the delta?
yeah, but the delta was very tiny.
It's still there. So my question basically becomes, do we even need to do physics anymore?
Yes, because your basis does not contain
Yes.
enough information. The free, you cannot do perturbation theory on a plane wave basis unless your interaction is very soft.
I would hope so, yeah.
So you still need to do physics. Fortunately, otherwise you would be jobless.
Mhm.
Which might happen anyway because of AI.
Okay, are there other questions? Let me just check online.
It still said 8.
There's a comment from an online viewer. Danny says this is the best talk you've ever given.
Other questions? Okay, now let's thank Danny once again.
Our slides are also on the.
Okay.
No, you can't make our advisor. We can make our advisor go slides. You can't make.
Was unaware.
I
don't have access to the Zoom at that moment because I think it was sent to my FRIB email, which doesn't work on my laptop this week.
Awesome.
Apparently.
There's a meeting I did.
Your advisor was here. He's in the. Have him do it.
Oh, yeah, that'll be great. Have a delay.
Look, I had to deal with the one frame rate.
Yeah, the ID is 7379440.
Okay, I can do that though. I guess we have time.
I think it's easy.
Yeah. We still have extended before start.
What was it again? 7-3?
7379440.
Going for some reason. Just forwarded it. Okay, I'll do that. Maybe you're acting as my FRIB email today.
You can set your,
I know. It used to work.
well, so you can't redirect anymore. They
Okay.
disabled that, but you can forward a copy,
Okay.
which I promise is very annoying because it fills your inbox with emails from you with the subject line that's obfuscated. So you can't really, you have to actually read them. You can't just skim them,
Oh, I see.
but it's better than having to log into your account. Please be on the YouTube channel again. Awesome.
Included this.
I will force our undergrads to watch.
Fantastic. Oops.
Official verdict on your employees, Steve. I didn't send you my slides before, so didn't get your official seal of approval. His has a funding attribution statement, so it's even better than both of ours.
He used the.
Yeah, excellent.
Actually, wrong.
So our next speaker is Ben Clark, also from EPRIB MSU, and he'll speak about emulating the Magnus formulation of IMSRG.
Alrighty, so I'll try to be quick because I'm sitting between you and lunch. So just to give a brief outline of what we're going to talk about. So we're going to go over the background motivation for this kind of work. We're going to talk about current emulation techniques for the Magnus formulation of IMSRG. And then we're going to talk about what we've been up to using PMMs to emulate this method. And then we're going to get into some preliminary results. Starting off with the background and motivation. So what is IMSRG? So IMSRG is a method that you can make an expansion of your Hamiltonian in the order of its interactions. So in the order of different creation and annihilation operators. And you can either band diagonalize or block diagonalize your many body Hamiltonian. So then it's easier to solve in the full space later if you want to do some kind of configuration interaction or what have you. So it's trying to find some unitary transformation that will transform your Hamiltonian so it's easier to solve later. And the way that we do this is kind of the heart and soul of the IMSRG method is computing this normal ordered commutator. So we have this generator that we call eta, and we have our Hamiltonian. And like I said, they're expanded and truncated at a certain order of force. And then they're normal ordered with respect to some reference state. And then we do a bunch of these normal ordered commutator terms. We have to solve this differential equation in order to figure out how our Hamiltonian is transforming under this unitary transformation. However, these calculations are pretty expensive. So this just doing one of these normal ordered commutator steps here is roughly into the 6, where n is the size of your single particle basis. You can do slightly better than that, but that's kind of roughly what it is. So we have to do a lot of these steps in order to solve our problem. So emulation techniques come in to have less of these. Yeah. So the purpose of IMSRG, typically you use IMSRG to make your Hamiltonian look nicer so that you can then extract observables from it later. So a problem with the direct flow of IMSRG is, which is what I've been describing to you now, is that if you ever want to get any observables, you have to co-evolve your observables with the Hamiltonian, which can get expensive pretty fast. And also you have to use your generator values that you got from evolving your Hamiltonian. These generator functions can be like on the scale of hundreds of megabytes or gigabytes. And so if you want to observe, if you want to look in an observable later, you have to store all those, which can get expensive. So in order to supplement this, a few years ago, some people at MSU started talking about the Magnus formulation of IMSRG, where you say that your unitary matrix that you're using to transform your Hamiltonian has an explicit form, namely e to the omega. And this has the advantage that once you figure out what e to the omega is, you can just transform any observable that you want. You don't have to re-evolve the entire thing using this expensive BCH formula with a storm ordered commutator. So this is a pretty nice method to have. However, emulators have currently struggled to emulate the Magnus operator for IMSRG. So that's what we're going to talk about. So yeah, on current emulation techniques. So there was a lot of initial success using dynamic mode decomposition, as we've already kind of mentioned dynamic mode decomposition on the direct flow version of IMSRG. So these figures here are from Jacob Davison's thesis, the grad student that was there right before I got to MSU. And so as you can see here, if you look at these extrapolation values, so these are the energy values as you're flowing the renormalization group method, you can see that you get pretty good agreement. Qualitatively, it kind of follows the same type of form. And so, yeah, it works pretty well, even for even more complicated interactions. And you can see that you can cut off. So here we're flowing up to the flow parameter s equals 20. And if you cut off just at s equals 1, you can get most of the extrapolation pretty well. So it was a pretty powerful method. However, it struggles with predicting the Magnus operator for IMSRG. And it's also hard to modify so that you could maybe try to get it to do better. However, it's pretty accurate, and you can also train it pretty fast. Pretty much all you have to do in order to train DMD is invert a matrix. So we're looking for maybe a similar solution that can do the Magnus operator for IMSRG. So just to show you where DMD kind of fails for the Magnus formulation of IMSRG. So this is a figure where if the blue region is the snapshots that were taken, and then you can see the extrapolation. You can see as soon as the extrapolation starts, you start seeing a big divergence between the real answer and the emulated answer. You can do slightly better if you get later snapshots, but if you get snapshots that are too late, you kind of wonder, why are we emulating this in the first place? You don't want to, emulate, you don't want to get, most or half of the flow just to emulate it from there. Also, some people have tried to use neural networks to try to simulate this, and it works okay. However, I probably don't need to tell this group that neural networks can get kind of expensive computationally. They're hard to train. They can use up a lot of VRAM. And even though we could get pretty accurate results with this, you still have to use a lot of training data. Okay. So now we're going to talk about how we use PMMs to help solve this problem. I guess I don't have to explain what PMMs are because I'm like the third talk in a row talking about it, maybe fourth. So our approach to this basically was, in order for like as Patrick was saying, in order to use PMMs, you kind of have to know the form of your underlying equations. Well, with some of these IMSRG problems, it's kind of hard because, if we would know it, then we would know it, but it's kind of, you just have to do these nonlinear differential equations and then kind of figure out what your function looks like. But in general, what the Magnus formulation of IMSRG does is it says that, because we always know that you could model your IMSRG flow as some kind of Dyson series, but the Magnus formulation just says that it converges as the Magnus operator. Well, also, you learn in quantum mechanics when you're first learning perturbation theory, you learn that any time-dependent Hamiltonian, if you want to predict the ground state as it evolves through time, is some kind of Dyson series. However, whenever you're doing quantum mechanics, in a class, you don't typically have like numerical Hamiltonians that you can just diagonalize using NumPy. So you have to do these complicated formulas. However, if we can use PMMs to figure out a kind of an effective time-dependent Hamiltonian, where if we took the ground state evolution through time, we would get just our Magnus operator, since they both kind of follow this nonlinear Dyson series type deal. So in order to do this, because we're trying to emulate an operator using an eigenvector, there's a couple of hoops that we have to fly through. Eigenvectors are normalized. The Magnus operator, there's no reason for it to be normalized. So what we do is we fit a function to the normalization values of the Magnus operator. And it was a lot easier than we expected it to be. It turns out to just follow a hyperbolic tangent curve like surprisingly well. And then we designed this PMM that I'm calling P of S over here. You have some steady state part A, and then you have some dynamic part that's B. And then we just say that it moves as a function, it moves as the derivative of the norms. So if we can fit the norms, we can just take the derivative pretty easily. And then we have this loss function here where the loss function is just overlap between the ground state eigenvector of this PMM and the Magnus operator. And then of course, we have to subtract because Magnus operators aren't normalized. So we have to subtract with the normalization so that we get 0 when we're at the right answer. And yeah, so we're going to get into some results that we've.
We have to get the norm just because of this loss function that you need the norm of the Magnus operator, or there is a fundamental reason why you need the norm?
Yeah, so the loss function works a lot better if you can use an overlap like this. But the problem is that like if the Magnus operator were normalized, this would just be 1 minus the overlap so that you can know that they're overlapping, within a phase. But since I'm trying to emulate the Magnus operator using an eigenvector, and the Magnus operator is not normalized and an eigenvector is normalized, you have to subtract by the norm so that whenever the loss function is optimal, it's at 0.
No, yeah, but we would use the quantum fidelity, for example, right? Doesn't care about the normalization, which is basically the scalar product of your vector and another one divided by their norms. So it's going to tell you whether two states are the same, except for a global phase and norm you don't care about. So that's why my question I'm asking is whether do you need this norm just because you want to use this loss function, or you need the norm then afterwards to apply these Magnus operators to compute observables?
Oh, right. Yeah, I think that, so we were actually having problems with getting the training to converge without using this function. This function gives you the norms. So y of s is a function of the norms. So without using this kind of construction of the PMM, it wasn't, the training wasn't converging. So then, yes, it's like you might as well put in the loss function.
The norm of the Magnus operator is important to have reproduced.
Okay. Thanks.
All right, so some preliminary results. So we started out just using the pairing model, throwing some pair breaking at it, and also adding a perturbation with the formula in the middle there. And as you can see, the PMM predicts it quite well. So if you look at this graph on the left, this is the flow of the energy values. And then the blue line is where we cut off the training. So around s equals 3 out of 10. And so if we extrapolate from all the way to s equals 10, then you get the correlation plot that you see there on the right. It looks pretty much just like a straight line. And then if you look at the bottom, these are specific parts of the Hamiltonian that we're interested in. You can see the differences, and they're all pretty much negligible, even for a very small amount of training points. We can't do less than 4 training points because the fit that we have to do for the norm requires 4 parameters. So that's as low as we can go. But even then, we still get pretty good results. We use this to try to emulate IMSRG for infinite matter calculations. So this is a correlation plot, also stopped at flow parameter equals 3, extrapolated out to flow parameter equals 10. And you can see that you get a pretty good correlation plot. And this is also impressive because this is 988,416 parameters that we're trying to emulate, and we did it with just one complex 16 by 16 matrix. We were also trying to use PMMs to flow the spin squared operator for the pairing model. And then, so this table is a bit messy, but so if you look at the different columns, you have CI, which is the exact answer. And then, so here we have IMSRG and then IMSRG DMD. So IMSRG DMD is basically using the DMD, what do you call it? The DMD operator of IMSRG in order to get the generators so that you can then flow the different observables. It's a bit more cumbersome because you still have to do almost all the work of a normal IMSRG flow in order to get these expectation values. So keep that in mind. So you can see that IMSRG DMD, it's more expensive, and it's also not reproducing the IMSRG values quite as well, but the Magnus operator and then the emulation of the Magnus operator, they're a lot closer, and it's also a lot cheaper if you can get the emulation of the Magnus operator.
I'm sorry, did you say that the DMD was not reproducing the values so well? It seems that it's.
I mean, no, it's doing fine. The Magnus operator, the emulation of the Magnus operator is doing better though. Just for this, so the most interesting case here is this first excited state with pair breaking. And you can see that there's just a mild deviation there.
The DMD is, am I not reading this right? The DMD is, I mean, they're very, very close, both of them, but 3 9s and then a 7 versus 3 9s and then a 2.
Yeah, I mean, it's close.
I just want to make sure I'm not reading this wrong when you said that it's not doing as well as the PMM. I think it is doing better than the PMM. Do I not?
The emulation of the Magnus operator is just a bit closer. 2v2. It's not a huge deal.
The exact answer was 2 though. 2.0.
Right, but we're trying to emulate the specific, so.
That's which ones.
Right, so it's a
Oh,
bit,
you're not trying to get the CI
right.
answer. Okay, my bad. I was reading it wrong.
You know, IMSRG is kind of already approximation, so we're trying to approximate our approximation as best as possible, so. Right, I mean, there's a subtlety here, but yeah.
Thanks for explaining that.
Just showing reproducibility. Okay, so with that, conclusions, PMMs seem to find a balance between the speed and simplicity of DMD while also maintaining flexibility and accuracy of maybe something like neural networks. They can also accurately store a compressed version of the Magnus operator for the IMSRG flow, maybe letting us do some kind of uncertainty analysis in the future. And although we need to do further testing to figure out how much speedup is gained using PMMs, it should be more speedup than neural network methods with less parameters, probably somewhere in between, probably comparable to DMD, although I need to do more work to substantially make that claim. Yeah, and in the future, we would like to just do more crazy interactions, more crazy systems for PMMs and optimizing quantifier speed up, and then, yeah, maybe do some uncertainty analysis stuff. All right, and here are my references. Thank you.
Great talk. Are there questions? Yeah.
So sometimes it is also a non-linear problem, right?
Right. Yeah.
One could do this also now for coupled cluster, time-dependent coupled cluster, right? That's non-linear.
Morton would love to have a conversation.
Right?
Morton.
Good. I don't know. I don't know much about time dependent
This
cluster.
is so similar.
Yeah.
Mark's been trying to get us to do this.
Every meeting.
Stated.
Time dependent. Morton, I have
Yes,
3
on
other things
that,
I
yeah,
have to do.
we have that, yeah.
Is Morton in the Zoom call? No.
I didn't see it right now. Are there other questions? Yeah, Dan.
You go back to like the slide where it's showing the training data. So you kind of gave it where it already converged.
Right. So the thing about
Not really.
yeah, so this is kind of this happens like all the time when we talk about emulators for IMSRG. So if you look at the energy extrapolation, it's probably not that impressive. But the fact is that we're trying to emulate how an entire Hamiltonian is changing during the flow, and actually you'll see that the matrix elements of the Hamiltonian still had a good way to go. I pretty much just, yeah, you're right, this slide is not that impressive. I just kind of included to give you some visualization of showing that PMMs are kind of getting the general form right. And you can actually see where we stopped the training data. But there's still a lot more work to be done kind of in the other matrix elements. But yeah, you're right.
Maybe in other words, even if you had used the flow to train, you will still gain in a sense that you will know the operator now, and then you can apply it cheaply to any other observable.
Right, yeah.
Yeah, one thing I might be curious to see, if you plot your S squared expectation value as a function of the flow, is it already converged at S equals 3 or?
Yeah, so these results so far really aren't impressive. These, like I said, I put preliminary on here because we haven't done anything. I mean, this part, I would say that some of these results are kind of impressive, but the observable parts, yeah, they don't really move a lot. But the kind of the bright side is that you can see that the emulator is preserving the symmetries that are like inherent in the problem. So, I mean, the first excited state pair breaking, it does actually evolve a little bit, and you can see that there's some reproducibility. I didn't make that graph because, again, I think that we can do better problems than this. But yeah.
There's no parametric to this yet, right? The Hamiltonian parameters are fixed, your LECs.
Yeah.
Okay, so we've talked before about this, but I didn't think it fully through until now. So your reformulation of solving for Magnus in terms of an eigenvector, how do you plan to bake in the Hamiltonian parameters when, you know, the true solver is not an eigenvector? So
Right.
the way that this eigenvector will depend on parameters might be very, very different.
Right.
Do you know, have you looked into the future?
I do not know.
Crystal ball? Okay.
Yeah. That's a great question.
Because that's the coup de grace, right? If,
Right,
if
right.
we can get LEC extrapolation going or interpolation.
But I had a question. So let's suppose somebody, after the fact that you've done all this PMM emulation, gives you another operator that you hadn't seen before. How much extra training do you need to do to
So like still an IMS or G problem?
yeah.
So if we, are you saying if we, well, if we,
A new observable. You
Right.
want to measure like R to the fourth power.
right.
Or something like this.
It would be no work. You would just get you would just have the PMM and then you would extrapolate to the S that you want and then you would project it and then you would just do one DCH step to do the transformation. Yeah.
Because you would have the Magnus operator.
Right, you would have the Magnus operator and then you could, band diagonalize it or whatever you wanted to do for the next people to observe. Yeah.
Are you doing the PMM flow? So when you get the emulated Magnus operator, are you using that in the latent space or do you project it back to the full space and then apply it?
We have to project it in the full space and then apply it. Yeah.
Questions?
Is it exist any uncertainty for PMM?
Sorry, what was that?
Is there exist any uncertainty bound in your PMM in your result?
Uncertainty of the PMM? No, not at the moment. Like how much uncertainty the emulation adds? Is that what you're asking? Yeah, no, we haven't looked into that yet.
No, wait, let me just check. No other questions? Let's thank Ben once again. So we are now going to go into our lunch break. So we break until 1:30 Central Time. And one option is to go to the cafeteria. I guess a lot of us will just walk over there together. Or you wanna-
all our stuff here?
I think so, right, Bob? We can leave our computers here now. I don't see why not. We're behind the fence, you know, maybe trust other people in the room. I have to say, oh, sometimes, then you got it, right?